Welcome to Super Easy Physics and Mathematics, SEPAM. You are expected to answer 4 questions for a total of 40 marks. Question 1. A student determines the mass of a meter ruler by a balancing method. He is using the apparatus shown in Figure 1.1. Question 1a. The student places a circular load on the meter ruler shown in Figure 1.2. Determine the distance d of the center of the load from the zero end of the ruler, as shown in Figure 1.2. For 1 mark. The distance, d must be measured from the center of the load. Step 1. Determine the diameter of the load. The diameter is 29.5 cm minus 26.5 cm. The diameter of the load is 3 cm. Step 2. Divide the diameter by 2. Half of 3 is 1.5 cm. Step 3. Add the 1.5 to 26.5 to give distance of 28 cm from the 0 mark of the ruler. Distance, d, is equal 28 cm. Question 1, b, I. The student adjusts the position of the meter ruler on the pivot until the meter ruler is as near as possible to being balanced. Describe a technique for ensuring that the ruler is as near as possible to being balanced. Balance point of the ruler is between where it just tips one way then the other when it is placed on the pivot. Let's watch video on how to balance the meter ruler on the pivot.
So we want to find the center of gravity of this ruler. This is the 9th edge. So how do you do that balancing? So if you look at it, it's tilting towards the right. So what you need to do, you pull it from the side is tilting towards gently. Okay, right. So right, near balance. So it's balanced. But if it's tilting towards the side while, okay, so pull it out like 1 millimeter out of that, the left hand side is tilting towards the right. Pull it gently 1 millimeter away from that side, so it's near balance. So this is how you get the balance points, right? Okay, very good. Okay, so it's balanced.
Question 1, b, 2. The student finds that the ruler is as near as possible to being balanced when the pivot is at the 47.6 cm mark. Calculate the distance, a, of the center of the load from the 50 cm mark, as shown in Figure 1.1. Use your value of d from 1a, and the equation. A equals 50 cm minus d. For 1 mark. A is equal 50 cm minus 28 cm. A is equal to 22 cm from the center of gravity of the meter rule. Calculate the distance, b, of the center of the load from the pivot, as shown in Figure 1.1. Use your value of d from question 1a, and the equation. B equals position of pivot minus d. For 2 marks. B equals 47.6 minus 28 centimeters. Distance, b, is equal 19.6 cm. Question 1, c. The student moves the load so that its center is above the 5 cm mark and balances the meter ruler. He repeats this procedure for the load at the 10 cm mark, 15 cm mark, 20 cm mark and 25 cm mark. His results are shown in Table 1.1. Question 1c. I. Plot a graph of A, with unit as centimeter on vertical axis against B measured in centimeter, on the horizontal axis. Use the values in Table 1.1. You do not need to start your axis at the origin with coordinates 0, 0. Draw the best fit straight line. For 4 marks. Draw the vertical axis and label it B. Use the scale of 2 cm to 5 units. Start the axis at 25 cm and end it at 45 cm. Draw the horizontal axis and label it B. Use the scale of 2 cm to 5 units. Start the axis at 20 cm and end it at 45 cm. Secondly, do the plotting of the coordinates. Plot point 40.5, 45 on the vertical axis. Plot point 35.2, 40 on the vertical axis. Plot point 31.5, 35 on the vertical axis. Plot point 26.0, 26 on the vertical axis. Plot point 22.5, 25 on the vertical axis. Thirdly, draw the line of best fit. This is a line that shares all the plotted points into two equal distribution to the right-hand side and left-hand sides of the line. Question 1c, 2. Determine the gradient, g, of the graph. Show clearly on the graph how you obtained the necessary information. 4-1 mark. The gradient of the graph is change in vertical axis divided by change in the horizontal axis. Indicate the triangle on the graph. Gradient is the difference between 45 minus 33 divided by 40 minus 29.5. The gradient is 12 divided by 10.5. The gradient is 1.14. It is a ratio. It has no unit. Question 1, D. Calculate the mass m of the meter ruler using the equation. M equals to K divided by G take away 1. Where K is equal 25 gram. Give an appropriate unit. 4-1 mark. Mass of ruler is equal to 25 gram divided by the difference between 1.14 and 1. Mass of ruler is equal to 178.57 gram. Question 1, E. The accuracy of the result obtained by this procedure depends on the meter ruler, without a load, balancing with the pivot at the 50 cm mark. A student finds that this does not happen. She adds a small piece of modeling clay to one end of the meter ruler to correct it. Suggest if this is a suitable change for this experiment. Explain your answer. 4-1 mark. There are two possible answers. No, because mass of clay increases mass of meter ruler. Yes, because mass of clay is only a small percent of the mass of meter ruler. Question 2. A student investigates a circuit containing different combinations of 3 resistors. She first uses circuit A, shown in figure 2.1. 3 resistors are connected in series with an ammeter. Question 2a. On figure 2.1, draw a voltmeter connected to measure the potential difference, PD, V for terminals P and Q. 4-1 mark. The voltmeter is connected in parallel across the terminal P and Q. Question 2b. The student measures the potential difference V for terminals P and Q and measures the current I in the circuit. The meters are shown in figure 2.2 and figure 2.3. Read and record, in the first line of table figure 2.1, the values of V and I shown on the meters in figure 2.2 and figure 2.3. The voltmeter in figure 2.2 reads 3.1 volts and the ammeter in figure 2.3 reads 0.12 amperes. Question 2c, I. Calculate and record in table 2.1 a resistance R for each circuit. Use the values of V and I from table 2.1 and the equation R equal voltage divided by current for 2 marks. The resistance of circuit A is calculated by dividing the potential difference of 3.1 volts by current of 0.12 amperes to give the resistance of 25.83 ohms. The resistance of circuit B is calculated by dividing the potential difference of 2.9 volts by current 0.22 amperes to give the resistance of 13.18 ohms. The resistance of circuit C is calculated by dividing the potential difference of 2.6 volts by current 0.86 amperes to give the resistance of 3.83 ohms. Question 2c, 2. Add units to the column headings in Table 2.1. For 1 mark. The unit of potential difference across the resistors is volts, the unit of current is amperes, and the unit of the resistance is ohms. Circuit B. The student connects the resistors between terminals P and Q as shown in Figure 2.4. She measures and records, in Table 2.1, the values of V and I for this circuit. Circuit C. The student connects the resistors between terminals P and Q as shown in Figure 2.5. She measures and records, in Table 2.1, the values of V and I for this circuit. Question 2, D, I. Calculate a resistance across circuit A, use the value of R from circuit A and the equation, resistance A is the effective resistance of circuit A divided by 3. Resistance of each resistor in A is 25.83 ohms divided by 3 to give 8.61 ohms. Calculate a resistance of each resistor in circuit B. Use the value of resistance from circuit B and the equation. Resistance of each resistor in circuit B is equal to resistance of circuit B divided by 1.5. Resistance of each resistor in circuit B is equal to 13.182 ohms divided by 1.5 to give 8.8 ohms. Calculate the resistance of each resistor in circuit C, use the value of R from circuit C and the equation. Resistance of each resistors in circuit C is equal to 3 multiply the effective resistance in circuit C. Resistance of each resistors in circuit C is equal to 3 multiply 3.023 ohms to give 9.1 ohms. Question 2, D, 2. A student suggests that RA, RB, and RC should all be equal. State whether your results support this suggestion. Justify your statement with reference to values from your results. For 2 marks. Statement. Yes, the results support the suggestion of RA is equal to RB and RC. Justification, within the limit of experimental accuracy. RA is equal to 8.6 ohms is approximate 9 ohms. RB is equal to 8.8 ohms is approximate 9 ohms. RC is equal to 9.1 ohms is approximate 9 ohms. Question 2, E. A student investigates the resistors in circuit A using a variable resistor to change the current in the circuit. Question 2, E, I. In the space below, draw the symbol for a variable resistor. For 1 mark. The circuit symbol of variable resistor is a rectangle pierced by an arrow. Question 2, E, 2. Suggest one advantage of using a variable resistor to change the current in the circuit. The use of a variable resistor makes it easy to obtain different range of values in the circuit and easily change the values of current flowing in the circuit. The total marks for question 2 is 11 marks. Question 3. A student determines the focal length of a converging lens by 2 methods. Question 3a. The student sets up the apparatus as shown in Figure 3.1. Suggest one precaution that must be taken when setting up the apparatus to ensure accurate measurements. For 1 mark. The illuminated object and lens should be at same height above the bench. Lens and screen should be perpendicular to bench. And meter rule should be fixed to bench. Question 3b. The student sets the object distance U between the illuminated object and the lens to 20 cm. He places the screen near the lens and moves the screen until a sharp image of the illuminated object is seen on the screen. Question 3b, I. Describe a technique for obtaining an image that is as sharp as possible. For 1 mark. Move screen slowly back and forth. Let's watch the video clip of how to obtain a sharp image.
And so that then you have the meter rule. There is a meter rule between the rail bus and the screen. Okay, so how do you obtain the image formed by the object, which is the mesh here? So all you need to do, get the object distance, which is the distance from the lens to the ray boss. Then the next thing you're going to do, let's fix it at 28 cm for the lens. That is the object distance. U is 28 cm. So let's see where we can have the image. So how do we get the position of the image, or to obtain the image distance? You move the lens back and forth until you have a sharp image. So let's see. It's getting blurred. So move it closer till you have some. This is a sharp image. So what do? How do you get? So you can now move the ruler to this, to get this. So that gives us about 86 cm.
Question 3b, 2. Measure the image distance v_1, the distance from the lens to the screen on figure 3.1. The image distance measured with a ruler is 8 cm. Figure 3.1 is drawn to 1/10 scale. Calculate image distance v_1, the actual distance from the lens to the screen. For 2 marks. The actual image distance is 8 multiplied by 10 to give 80 cm. Question 3c. The shapes of the illuminated object and the image seen on the screen are shown full size in figure 3.2 and figure 3.3. Question 3c, I. Measure the height of the illuminated object, as shown in figure 3.2. The height of the illuminated object is 1.2 cm. Measure the height of the image on the screen, as shown in figure 3.3. The height of the illuminated image is 4.8 cm. Question 3c, 2. Calculate a value m for the magnification, using the equation. Magnification is equal the height of image divided by the height of object. For 1 mark. The magnification of the lens, m is 4.8 cm divided by 1.2 cm. The magnification of the lens, m is 4. It is a ratio. It has no unit. The magnification of 4 means that the height of the image is 4 times the height of the object. Question 3d. Calculate a value f_1 for the focal length of the lens. Use your values from section B, 2, and C, 2, and the equation. Focal length is equal to image distance divided by the sum of magnification and 1. Focal length is equal to 80 cm divided by 4 plus 1. Focal length is 16 cm. Question 3e. Describe one difficulty that is experienced when using a ruler to measure the height of the image in this experiment. Suggest an improvement to the apparatus to overcome this. For 2 marks. Difficulty: hand or ruler blocks light from the ray box when trying to measure image size. Improvement: use translucent screen and measure size image from back of the screen. Fix grid to screen to directly help to measure the size of the image.
One major difficulty of performing this experiment is your hand getting on the way. You block the ray. And then secondly, if you want to measure the image size, the ruler can get on the way. So for example, look at it. It's blocking the ray of light. But you can be careful about that. So let's see who can measure the size of the image. So this is about 8 cm. So, but if you want to correct this difficulty in performing the experiment, so the improvement on this setup is to use a translucent screen so that you can measure the size of the image from the back, or you use a grid, a screen with grid, so you can actually read up the value of the size of the image from the screen.
Question 3f. The student adjusts the position of the lens so that object distance is 40 cm and obtains a new value image distance, v_2, for the distance between the lens and the screen. If the corresponding image distance measured by the student is 25.1 cm. Calculate a second value, f_2, for the focal length of the lens, using the equation. Focal length of the lens equal product of object distance and image distance, divided by object distance added to image distance. For 1 mark. Focal length is equal to 40 multiply 25.1 divided by sum of 40 and 25.1. Focal length is equal to 1004, divided by 65.1. The focal length calculated by this second method is 15.4 cm. Question 3, G. Suggest which value of focal length, f_1 or f_2, might be more accurate. Explain your answer. For 1 mark. The first method gave the focal length of 16 cm while the second method gave the focal length of 15.4 cm. The value of the first focal length is greater than the value of the second focal length. The value of the second focal length is more accurate because it was obtained by measuring only object distance and image distance, which involves less error in measurement. Measuring the size of image and calculating the magnification of image formed in the first method entails more uncertainties in the process of obtaining the focal length of the lens. The total mark for question 3 is 11 marks. Nailed the concepts? Leave a comment below with the next topic you'd like to see tackled. Question 4. A student investigates the effect of insulation on the cooling of a liquid. Plan an experiment which will enable her to investigate how changing the thickness of insulation surrounding a beaker affects the rate of cooling of hot water in the beaker. The apparatus available includes a glass beaker, a supply of hot water, a lid to fit the beaker, strips of insulation which can be cut to size. In your plan. Step 1. List any additional apparatus needed. Step 2. Explain briefly how to do the experiment, including the measurements to take so that the rate of cooling can be determined. Step 3. State the key variables to keep constant. Step 4. Draw a table, or tables, with column headings, to show how to display the readings. You are not required to enter any readings in the table. Step 5. Explain how to use the readings to reach a conclusion. You may draw a diagram if it helps to explain your plan. Experiment plan, insulation and hot water cooling. Scoring point 1, name additional apparatus needed. Firstly, thermometer is needed to measure the temperature of the water. Secondly, stopwatch timer or digital timer is needed to measure the time interval during the cooling of the hot water. The third instrument needed is measuring cylinder to measure volume of hot water and pour into the beaker. Scoring point 2, how to conduct the experiment. Step 1, prepare the hot water. Boil water in a kettle. Using the measuring cylinder, carefully pour a specific volume 200 ml of hot water into the beaker. Record the initial temperature, set at 70 degrees Celsius, T0, of the water using the thermometer. Step 2, set up insulation. Cut strips of insulation to a size that can comfortably wrap around the beaker. I will repeat the experiment multiple times, varying the thickness of the insulation each time. Step 3, start the measurement. Place the lid on the beaker and carefully wrap single layer of the insulation around the beaker for the first trial. Start the timer. Step 4, record temperature. At regular time intervals, every minute, record the water temperature using the thermometer. Continue recording temperature measurements until the water reaches room temperature around 30 degrees Celsius or for 5 minutes. Step 5, repeat with different insulation thickness. Repeat steps 2 to 4, using a different thickness of insulation for each trial. Ensure the water is reheated to its starting temperature of 70 degrees Celsius, T0, before each trial. Scoring point 3, key variables to keep constant. There are about 5 variables that can be kept constant in this plan of experiment. Number 1, ensure the water starts at the same temperature for each trial. Number 2, use the same amount of water in each trial. Number 3, use tap water or distilled water consistently throughout the experiment. Number 4. Conduct the experiment in a room with a constant temperature. Number 5. Avoid stirring the water during the experiment. Scoring point 4, Table of Values. The first table has 4 columns. First column is the trial, the second column is the insulation thickness in centimeter, the third column is the time measured in minutes, and the last column is the temperature column recorded in degrees Celsius. Scoring point 5, Reaching a conclusion. By analyzing the data table, you can compare the rate of cooling for different insulation thicknesses. The rate of cooling can be determined by observing the change in temperature over time. A steeper decrease in temperature indicates a faster rate of cooling. Plot a graph. Plot a graph with time measured in minutes on the x-axis and temperature in degrees Celsius on the y-axis for each insulation thickness. This will visually represent the cooling curves. Compare the curves. Steeper curves, faster temperature decrease, indicate faster cooling. Conversely, shallower curves represent slower cooling. Conclusion: based on the graph and data, you can conclude how changing the thickness of insulation affects the rate of cooling of the hot water. Thicker insulation should result in a slower rate of cooling compared to thinner insulation or no insulation at all. Don't forget to like and subscribe for more. Feeling confident? Subscribe for more exam-busting physics and math tutorials coming soon. Aced your exam? Smash that like button and subscribe for more super easy physics and mathematics tutorials.